Thanks for coming. So today we're gonna hear something about algebra and lean by Seonghun Park, who is a student at the School of Computing at KAIST. So yeah, please.
Thank you for the kind introduction. Hello everyone, my name is Seonghun Park and I'm a master student in School of Computing at KAIST. In this talk, I will be presenting on work formalizing flag algebras in the Lin theorem proof. This work is a joint collaboration with Jihoon Hyun and Kyungwon Jang and Hong Seok-yeon at KAIST and Theorem at IBS. To begin, I will briefly explain what formalization means. It is the process of translating informal mathematical proofs into machine verifiable languages such as Lin, Rock, and Isabelle. There is a well-known example that clearly shows why formalization is important. It is called the liquid tensor experiment. In 2019, Peter Schulze introduced a new theory called liquid vector space. The proof of the key theorem in this theory was extremely long and complex, even though author himself was not fully convinced of the proof correctness. Because of this, Schulze asked the Lin community to check the proof using theorem prover. Many mathematicians and Lin users joined this project, and after about 1.5 years, the entire proof was fully verified in Lin. This example shows that formalization can be helpful when mathematical arguments become very complex and hard to check carefully by hand. Now, let me briefly discuss the advantage of formalization. First, formalization gives us absolute correctness. A computer checks every logical step, so human errors are eliminated. Second, it gives us reusable proof infrastructure. This means we can reuse existing proofs and building larger arguments systematically. Finally, it's a good opportunity to double-check our understanding. Formalization forces us to look again all steps that we already skip or take for granted. Of course, these benefits come with challenges. First, writing a formal proof requires much more time and effort than natural language proof. Second, it requires expertise in both mathematics and formal languages. One needs to understand the mathematics very well and also know how to work with the theorem prover. With this background, we formalize flag algebras. Flag algebras is a mathematical framework for symbolically expressing relationships between combinatorial objects. Using this framework, many open problems has been resolved, including triangle density problem, reduced pentagon theorem problem, and density of included five-cycle problem, and so on. Our goal was to bring these benefits of formalization to this powerful tool. In our Lin formalization, we closely followed the Razborov's original paper on flag algebras. And we formalized most of the core theorems in this paper. This formalization took roughly 1 year to complete and consists of about 19,000 lines of Lin code. So what can we do with this formalization? Using this formalization, we can transform flag algebra arguments into fully formalized Lin proof. Then what is flag algebra argument? Let's go through the basic idea. First, we need to define the concept of subgraph density. Throughout this presentation, all graphs are assumed to be undirected, simple, and finite. Let H be a graph with m vertices, and G be a graph with n vertices. The subgraph density of H in G denoted as ph, g, is the probability that when uniformly randomly chosen n vertices of G induces a subgraph isomorphic to H. For example, let's consider the case where H is an edge and G is a 3-vertex path. Then in G, there are 3 ways to choose 2 vertices. Among these cases, there is exactly one bad choices that induces a subgraph not isomorphic to H. Therefore, the subgraph density is 2 over 3. As another example, consider the case where H is a triangle and G is a graph with 4 vertices consisting of a triangle and one isolated vertex. If we choose 3 vertices in G, there are 4 possible choices and only one of them forms a triangle. Therefore, the subgraph density is 1 over 4. And Flag algebras provide an algebraic framework to express relationship between subgraph densities symbolically. For example, consider the following statement. For any graph G, this subgraph density is a probability value. Therefore, it must lie between 0 and 1. We can express this statement in Flag algebra framework. We just omit the explicit reference of G and the density notation P, and we can express it symbolically like this.
Do we work on only finite graphs or any other infinite graph is included?
Actually,
So I think technically we should consider large enough graph. So
Yes.
things has to be graph ones. But I think he's gonna just ignore it. Essentially everything is finite.
thank you. And we can express it symbolically like this. As another example, consider the following statement. For any graph G, we want to compute summation of these subgraph densities. When choosing 3 vertices from G, there are only 4 possible non-isomorphic subgraphs. These 4 graphs are the ones being only 4 possible non-isomorphic graphs. So the summation of these densities must be equal to 1. So again, this statement can be written as follows in Flag algebra framework. As a final example, let's look at how densities of small graphs are related to densities of larger graphs. Instead of calculating the edge density of G directly, we can compute it using the densities of 3 vertex subgraphs. This formula shows that the edge density is a weighted sum of the density of 3 vertex graphs. Each coefficient represents the edge density of that 3 vertex graph. For example, for the 3 vertex path, the edge density of this graph is 2 over 3. Therefore, so its coefficient is 2 over 3. This statement also can be expressed symbolically in Flag algebra framework. Now, I will explain a Flag algebra proof using Mantel's theorem as an example. Mantel's theorem states that for all graph G, if the triangle density of G is 0, then edge density of G is at most 1 over 2. This statement can be expressed in Flag algebra notation. And this code shows how we write Mantel's theorem in Lean. Here, K3 represents the triangle, and K2 represents an edge. In the second line code, there is an assumption of this theorem named by triangle 3, which states that K3 is 0. In the third line, after the first column, our goal is represented. We want to prove that K2 is less than or equal to 1 over 2. At the bottom, you can see the word sorry. In Lean, this is a placeholder that tells Lean to skip a proof for a moment. And we will fill in this sorry in later. Next, let's generate and organize identities and inequalities to prove Mantel's theorem. These are all the identities and inequalities needed to prove Mantel's theorem. The first three expressions are the ones we showed earlier, and the last inequality may look unfamiliar. As before, it means that for any graph G, the value obtained by computing these density calculation, the value is always greater than or equal to 0. To prove this inequality, we need an operator called the downward operator, but I will not explain how to prove this inequality in detail. So, and then, if we multiply the second expression by 1 over 3, and change the inequality in the third expression into an identity, so we get these three inequalities. Using these inequalities, we can complete the proof through algebraic computation. First, we add the three inequalities to obtain the following inequality. Since we assume that K3 is 0, the last term disappears. By grouping the coefficients, the red box's expression became equal to 1, so we can conclude that K2 is less than or equal to 1 over 2. So therefore, the proof of Mantel's theorem is complete. So I prepared a live Lean demo for this process. Let's move to Lean and see how to prove Mantel's theorem in Lean.
Is it proof the theorem or proof checking?
Proof.
So technically, you show how to prove, and you write them into that Lean language and check the proof, or they generate the proof.
No, he's writing a proof. Right?
Yeah, I will prove
so
the
checking it
Yeah.
technically.
Yeah. First, as I prepared all the expressions discussed in the slide using sorry, so you can see one is O3, and before, I will briefly explain the graph notation. Here, O3 means there is a 3 vertex graph with no edges. And E3 means 3 vertex graphs with 1 edge. And P3 means as you can see, the 3 vertex graph with 3 vertex path graph. And K3 means triangle graph. So you can see the relation. 1 is O3 plus E3 plus P3 plus K3. And relation 2, K2 is less than or equal 1 over 3 times E3 plus 2 over 3 times P3 and K3. And relation 3, 1 over 3 times E3 is non-negative, and the relation 4 is, as I mentioned earlier, unfamiliar inequalities, which can be obtained by downward operation in flag algebra. And also I prepared a lemma called flag add add, which allows us that add two inequalities while preserving the inequality relation. Then let's prove the Mantel's theorem in Lean. As mentioned earlier, the statement is follows. Assuming that K3 is 0 and our goal is K2 is less than or equal to 1 over 2. So you can see the Lean info view states that we have these assumptions and we have to prove this statement. And to make the calculation step explicitly, I used the tool called calc. So I have outlined the calculation steps in advance, and let's go through each step of the proof together. First, in order to add inequalities, we adjust the expression by adding 0. So we have to prove K2 equal K2 plus 0 plus 0. Since we already have the lemma such as add 0 doesn't convert any object, so we can use this in proof. So we can write proof as RW add 0. And before this comment, we have to prove K2 equal K2 plus 0 plus 0, and write the RW add 0. The 1 0 is disappeared. And one more, we can write add 0. Then there is no goal to solve, so we can remove this. The comment like this RW, which allows us to transform the current goal or reduce it to a simpler one using previously proven facts, are called tactic. And Lean also provides tactics that automate simple reasoning steps, for example called by sim. The sim tactic can automatically solve trivial calculation and rewrite. Next, let's prove addition of inequalities. As discussed earlier, we can apply this lemma, adding two inequalities. So we can just write apply flag add add. The apply comment means it's a tactic which turns the conditions required by the lemma into a new goal. So our goal is adding these three inequalities. So I will use this flag add. And as you can see, there is a new two goals to apply this flag at the array at. And for the second goal, you can see that these expressions are exactly same as the relation 4. Therefore, we can just write exact relation 4. So there is the word solve. And for the second inequalities, we can apply flag at array at one more time. Then make two new goals. And one is exactly same as relation 2. And one is exactly same as relation 3. So we can write just exact relation 2. Exact relation 3. Next, let's collect the like terms. To do so, we need another property, add-small and sub-small. This means distributivity of coefficients is handled by these add-small and sub-small. So let's use again symplectic, add-small, sub-small. Then you can see the coefficients are distributed using this line of comment. And then when we check the left hand side and right hand side, there is just something different using order of additive and order of associative. So all of these are proved by axiom of ring. So you can just there is a tactic called ring, which automatically solves goals followed from the ring axioms. Next, the next step is compute the coefficient. 1/3 plus 1/3 minus 1/6 is just 1/2. And this process can be just write num. This is also another automatic technique provided by Lin. This automatically handles concrete numerical calculation. Next, we will remove this case 3 by using the assumption triangle 3. It's same as before. Let's write just RW with triangle 3. Yeah, but you can see that this comment rewrites all of case 3 in the goal. But so we have to use another tactic called by NRW. This tactic allows us to pick specific expressions what we want to rewrite. So we just want to remove this second case 3, write NRW 2 with case triangle 3. So you can see only the second case 3 is replaced as 0. And we can complete the proof by add 0. The final step, at this point, the remaining step is just group the coefficients and rewrite the expression using relation 1, which means 1 is equal to O3 plus E3 plus P3 plus K3. We write relation 1. This make this one expressions to O3 plus E3 plus P3 plus K3. And then what we have to remain is just distribute these coefficients to each term. So using small add, the left distributive row. Using this row, we can conclude the final calculation step. And by doing so, we complete the proof of Mantel's theorem in Lean. And all of these lemmas used in the process are provable within our formalization framework. The actual proof is as follows. This means the universal, the set of all graph with three vertex graph, there is only 4 cases. Using these, we can prove relation 1 as follows. And 2, 3, 4. And for the rest of the talk, I would like to share an experience from our formalization process. Consider proving this statement. For human, it is quite obvious that this subgraph density is 2 over 3. However, when we tried to prove this in Lean, it turned out to be surprisingly hard. The proof required hundreds of lines of code. Why is this easy for human but difficult for Lean? When human compute the density, we might implicitly do the following. First, we think about all possible cases. That is, we consider all subgraph induced by choosing 2 vertices from the 3 vertex path graph in P3. Then we count how many of these cases satisfy the condition, namely whether the induced subgraph is isomorphic to an edge. The key point is that we implicitly understand all cases are finite, and then we enumerate all of them. In Lean, all of these implicit human reasoning steps must be written out explicitly. To show Lean that the set of subgraph is finite, we need to provide the following proof. The main let G be a graph with a finite vertex set V, then the set of all subgraphs of G is finite. The main idea of the proof is follows. Each subgraph is determined by its set of vertices, which is a subset of V, and its set of edges, which is a subset of V times V. Thus, we can define a natural injection F from all of subgraph of G to this power set of Cartesian of power set. And since V is finite, the product of power set is also finite. So we can prove that all subgraph set of all subgraph is also finite since f is injective. In Lin, this proof can be written as follows. We define the natural injection f as follows, and then we prove that f is indeed injective function. But the limit of this proof is that it tells that that the set of all subgraph is finite, but it does not tell Lin how to enumerate all the subgraphs. For this reason, the definition is marked as non-computable. This means mathematically the proof is correct, but from the computer's point of view, it cannot be turned into an executable algorithm that actually enumerates the all subgraph. This is one of the reasons why a subgraph density calculation that is simple for human but is difficult to prove in Lin. So we tried to find a way to rewrite this proof that allow for enumeration. And we encountered several issues, and one of the most important was the definition of a simple graph. The default definition of simple graph in Lin was not good for building an enumerative proof. The default definition of simple graph in Lin is not good. What? Yeah. So we changed this simple graph definition so that enumerative approach would become possible. This is an example of proof that enable enumerations. So from now on, I will refer to these this kind of proof as an enumerative proof. An enumerative proof consists of an algorithm that enumerates all elements. You can see the statement if then else. And then together with a proof that the algorithm indeed lists every element without omission. So by changing the proof in this way, we can make Lin to follow the implicit reasoning step of humans. As a result, Lin can now easily prove the things that is obvious for a human. So depending on which proof style we choose, the length of the code needed to prove the subgraph density calculation changes significantly. Using the enumerative proof, as you can see on the slide, the proof becomes quite simple. Just order to Lin, compute and compare the result value. In contrast, if we use the non-enumerative style, then we need to prove all these trivial steps manually. The code shown on the slide is only part of the proof, and the full code exceeds 100 lines. To summarize, we formalized flag algebra in Lin theorem prover and successfully applied this framework to prove Mantel's theorem as a case study. One of the main experience was things that are obvious to humans are not obvious to Lin. And one key solution is to make implicit human reasoning steps explicit for Lin. And also I realized that careful consideration of definition design and proof style is essential in formalization. And lastly, formalizing flag algebras gave me a much deeper understanding of the subject itself, and I believe this is one of the primary advantages of formalization. And I hope this presentation was helpful for those interested in formalization. And thank you for listening.
All right, thank you. Any questions?
Can we prove the Mantel's theorem by the enumerative proof that you mentioned?
Yeah.
But like Mantel's theorem says, like for any G, and like if G is not something concrete, what does the enumerative proof really do?
Actually,
Flag algebra proof only works for one.
Yeah. So
yeah.
flag algebra always,
yeah.
the output of flag algebra is only for big. I mean, it's a limit, right? In the limit, it's this density.
So also, the actual proof with all the things, the enumeration he talked about are, while using flag algebra, there are some cases where you need to compute certain things. These computations are done by the enumeration, not entire statement about this universal quantification for all G and so on. That's not handled by the enumeration. We handle only some special case. So sometimes you need to show that the edge density of a triangle is 1 and so
Okay.
on. So these are the kind of things that's handled by.
Like if that's at any step of the proof, like you have
That's right.
two concrete things, then
That's right.
okay. But it takes a lot of time for the enumerative proof to work itself out, right?
Here, no, because everything is small. It doesn't take
Like
much time.
usually it's small.
Yeah, here in this case, but
Ah, okay.
large
Maybe
case.
these graphs are much more bigger. Maybe the time are
Yeah.
Yeah, that's right.
extremely increasing.
So in the proof step, so you assume that for subgraph densities between 0 and 1, which is obvious to human, but
Yeah.
you write them as a lemma because machine cannot believe it is
Yeah.
true, obviously.
Yes.
But then we need to prove that thing in the lean. You also actually made a machine proof for the lean,
Yeah.
and then while you prove, I guess that you need to assume some obvious thing that you think which is obvious to human,
Yeah.
and then it goes to variation of like. I mean, it goes to very, very, very basic stuff, and then how can we? So at some point, I think you need to assume something. We cannot do everything. So at that time, what is the limit step of such thing? Like,
Something. What does this assume something?
yeah. So we go to every basic. We go to basic and so on. Then there should be some limit. We should assume something to prove everything. So, what is the last step, and how can we see this is obvious enough to assume the thing obvious enough?
Actually, when we write formalization in Lean, we made the definition for graph, and then calculating operator between the graph, and those those operations are right as we want to prove. So
Also, if we use Mathlib, which already formalize or axiomatize mathematics quite a bit, but if you go inside the Mathlib and check, okay, what are the real foundations? Real foundations depend on type theory with so-called calculus of construction. On top of this, they may formalize notion of sets, notion of functions, and so on.
I see.
So they
So
build
there is-
everything, but
there
it's
is a
already done.
library.
Yeah, it's already done. So we are living on top of
So
it.
you don't have to define integers.
That's
right?
right.
Already there.
Thank you.
Can you explain like how did you change the definition of simple graph from the original?
Yeah.
And like, how did that change made the enumeration possible?
Can you
Yeah, so you changed the definition
Yeah.
of simple graph, right?
Yeah.
So what? So what's the difference and what makes the computation easier? That's the question.
We changed the definition of the graph, and before the with basic definition, we had to prove all of these steps in manually. But using the computable definition of graph, we can just ask Lin to calculate these operation using given algorithm. So just compare the result of the value. So the result value is equal, the theorem is proved.
So some other comment is the original definitions. The edge of a graph is defined as a proposition which take two parameters, which are vertices, and then say whether they are connected or not. So it's a proposition, which means it's in the status of logical formula. On the other hand, in the new definition, edge is a something that produces a set of unordered pairs. So it's a bit like a Boolean expression. If you can run it, if you run it, you return a finite set of unordered pairs. So there are different flavors. One is more like a logical formula. The other is more like a finite set producing computation.
So just to get some intuition how robust this lean formulations would be. So if instead proving the Mantel's theorem, you would now take what you have and try to say, okay, suppose the edge density is strictly greater than half, can you prove a lower bound for the number of triangles? So if you run the flag algebra method, you can prove an inequality where you have the number of triangles is something which depends on p minus half by p edge density. How easily could you adapt this formalization to that sort of a, like, would you have to do a lot of extra work, or would it come quite easily?
So we already proved something called Gutmann's bound, which is the easiest case. I mean,
Okay, I think that's
Gutmann is
okay.
an easy case. That's already done.
So basically that's roughly the same amount of work as proving Mantel.
So I mean, because of the infrastructure, I mean, the proving Gutmann's takes like 3 days instead of a year.
Okay.
So, yeah. But
So
on the other
it's
hand,
easy.
if you want to go further, then there's actually Razborov proved the very tight lower bound. To prove the tight lower bound, you need, if I follow the Razborov, you need a so-called differential method techniques. That requires perhaps 6 months or something. So
Okay.
it's a completely different.
Good. Thanks.
I have one technical question. So while in your proving step, you calculate 1/3 plus 1/3 minus 1/6 is equals 1/2.
Yeah.
And you ask Lin to calculate it. And when we prove in mathematics, there is a lot of numerical, it needs a lot of numerical calculation, and after calculating it, the result is something. And if it is easy enough, like your case, we may ask Lin to just, after calculating this, the result is 1/2, something like that. But if it is very complicated, then maybe there is some boundary that Lin can check and Lin cannot check the its validity. So how strong that calculator or is the boundary? How can you check?
Actually, as you say, the complex calculation is quite not easy to ask Lin just to compute. So what we have to do is divide the problem up to Lin enable using automatic technique. So as you can see before, the calc tools are actually the tool to prove Lin this expression change up to this expression. Maybe you can do this using automatic technique, and then we write another expression, try to automatically prove.
Kind of making formal lemma for every each step of calculation.
maybe I hope those, as you said, the powerful automatic calculate tactic is provided by Lean. If then we can more easily formulate any mathematical calculation.
So is it possible in the future that the AI can reduce the lean code to verify?
Yeah, actually we are when we do the formalization, we use a lot of assist by AI called Gemini, GPT, and Copilot. So, but
How do you use it?
just ask them. I want to prove this statement in Lean. How can I write the code? But the answer, maybe the portion of the correct answer is at initial only 5%. Many of the results are not correct, even the codes are not compilable in Lean code. But we can insight or intuition from those answer and write using our intuition and specific code.
Yeah, also, it improved really a lot over the past 1 year. In the beginning, when he tried to use Copilots and the ChatGPT, the proof was, I mean, as he said, it's like a 5% or less. But now, when like a few days ago, I mean, like last week, when we played with it, it was much more useful. So maybe next year, I mean, it might be also, another thing I found very useful is that sometimes formal proofs are very cryptic. We use it. The tactics are a bit like instructions about theorem prover. You tell theorem prover how to prove certain theorems. So then if you just see the instruction, you cannot really figure out what's really going on. But then if you ask this Copilot and then explain what's really going on there, sometimes it gives a very nice explanation. So I found this very, very useful. And then maybe, as you said, 6 months.
This was mostly about verifying proofs, like us writing the proof and then like the Lean compiler going through it and verifying that everything's correct, everything flows from something. But what about like I have like half of proof, like some portions are missing, or maybe most of the portions, and then like is it possible like for Lean to like maybe explore or try to discover some proof? Like I have my goal and then some set of I don't know, axioms, and then from there maybe it tries to come up with a sequence of by and sorries.
Yeah.
And like it produces a proof.
Yeah, actually, we design the total proof using the sorry word. So.
You can use sorry as a space filler, but then if you really want to replace sorry automatically by a proof, so then maybe LLMs the one they can use. And there are some tactics, very popular tactics like a grind and so on. They are something called a version of SMT solver. So some specific kind of problems, if by calling tactic, it automatically take care of some of the proof obligations. A really big proof obligation, wait a year and then try Copilot and you might get an answer.
What about okay? I mean, I guess there are a lot of structural graph theories here. Have people been writing proofs in Lean in structural graph theory area?
Too lazy.
But Linda last year or something.
I think there's
French
more.
people are interested.
I think there's more matroid
Yeah,
theory
matroid theory people
than graph theory, because for some reason, like matroids are kind of better in MATLAB than graphs.
So something that we found when we formalize graph is that, I mean, usually people think graph up to the equivalence class, like implicitly assume it's a quotient space by isomorphism. But if you formalize it in Lean, then you have to make all these things explicit. Sometimes that can be quite painful.
I'll add something. So Yeah, so normally to find these flag algebra proofs, you have to solve some semi-definite program. So it would be nice if you could kind of have an interface between something like Flagmatic
Yeah.
and
Yeah.
what you're doing. Like,
Actually, our middle final goal is the using the result of Flagmatic certificate, just translate those certificates to lean proof automatically. So that's what we are trying to do.
Why is there a time zone?
Actually, the flag algebra is a vector space with multiplication, and this one is the multiplicative identity in those vector space. So, one is a unit vector for those vector space, and 1/2 is a coefficient for multiplied by
So
scalar.
it's a unit of a ring. Yeah, that's what one.
Any further questions? Okay, if not, let's thank the speaker.